So this problem is required to find the plastic moment of resistance for the given load factor. What is the load factor? So it is like a factor of safety. The factor of safety is the ratio between yield stress to the working stress. Like the load factor is the ratio between ultimate load to the working load. Ultimate load to the working load, which is the load factor. So if the working load is given, we can find the moment of resistance in the safer side by multiplying the working load with the load factor. So in this problem also we are going to multiply the all loads with the load factor. And also we have to decide how many number of mechanism is needed. So the number of mechanism is calculated by the number of redundancy and number of possible hinges. If the number of mechanism is identified with small n, number of mechanism identified with small n, capital N is the number of possible hinges, R is the indeterminacy, redundancy. We can find the number of mechanism is capital N minus small r. That is number of possible hinges minus redundancy. So we can find the number of redundancy. Here it is 2, 1, 3 and 4. 4 is the total number of unknowns, 2 is the equilibrium equation. So number of redundancy is 2. And number of possible hinges, first of all under the loads 1, 2, 3. 3 hinges is possible under the loads. 4 and 5 at the fixed support. 4 at the intermediate support, 5 at the fixed support. First one is under the UDL 5 kN per meter. Another one hinge is at 60 kN. Another hinge at under the 90 kN. Further intermediate support is also having resistance. So the possible hinge at B and the possible hinge at A. So the number of possible hinges is formed at A and B, D, E and under the load of 5 kN per meter under the span of AB. So totally 5 number of possible hinges. So 5 minus 2, 3 is the number of mechanisms. We have learnt about the types of mechanism, beam mechanism, column mechanism, combined mechanism, cable mechanism. So this section is completely beam. So in this we can find 3 number of individual mechanisms. So first mechanism is under this span. Second mechanism is under the 60 kN load of span BC. Third mechanism under the 90 kN load of span BC. So these are all the 3 different mechanisms. And what are the possibility of hinge formation and at the support, fixed support, and at the intermediate support and under the load. Here at the intermediate support, under the load, there is no possible hinge here because of the simply supported condition. Here at the intermediate support, under the load, there is no possibility of hinge here. And we should make clear the theta will be available here. Here also one theta will be available. So theta and theta will be available. And it is mentioned that for the span AB, moment of resistance is MP. The second span BC, the second mechanism indicates theta at support B and here also theta. But here the angle will be different because of the different span. So theta 1 will be here. So here theta 1. So under the load we can find some different deflection. So you should note that here left side theta, right side will be the different angle of section, angle of inclination because of the different span. So it is theta 1. In this condition, the third mechanism is under 90 kilonewton. So if I specify here it is theta, here it is theta 1. So under 60 kilonewton load we can find some deflection, different deflection. So first of all we are going to find the delta here because it is used in internal work done. So delta, you can take the separate triangle delta. The span is 12 meters, so 6 meters is at the middle. So delta is equal to, here it is theta. So delta equal to 6 theta. Delta equal to 6 theta. For the next triangle, in this triangle, here the spans are 8, 8, 8. So the deflection is equal to 8 into theta. So it is 8 theta. But here it is theta 1. Here it is theta 1. And here it is 8 theta 1 because the distance is 8. So if you find the deflection here, theta equal to delta by 8. So delta equal to 8 theta 1. 8 theta 1. So we should find some relation between theta 1 and theta. How we can find the relation between theta 1 and theta? So if you relate this triangle, if you relate this long triangle, already the deflection here is 8 theta. But if you compare this 16 meter span with theta 1, here we can find another delta of 16 theta 1. From this triangle, from the left side triangle, we can find 8 theta. From the right side triangle, the span is 16 meter and the angle is theta. So tan theta equal to 16 by delta. So theta equal to 16, delta equal to 16 theta 1. 16 theta 1. So for one particular position, we have two number of values, that is 8 theta, which is equal to 16 theta 1. From this we can find theta 1 is equal to 8 by 16 theta, which is 0.5 theta. Theta 1 is equal to 0.5 theta. We can make use of this relation between theta 1 by theta when substituting with the numerical values. Okay, this is all about the second diagram. For the third diagram, similarly, for the third diagram, if you separate this triangle, it is 16 meter. Here it is theta. So delta equal to 16 theta. But using the small triangle here, it is 8 theta 1. 8 theta 1. You can compare 16 theta with 8 theta 1. So theta 1 equal to 2 theta. In the last diagram, we can use this relation theta 1 equal to 2 theta. In the second diagram, we can use the relation theta 1 equal to 0.5 theta. In the first relation, there is no complication like theta and theta 1 here. But also you have to note that for the first span, the value is MP. But the span BC, here there is the value of 2 MP. There is the value of 2 MP. It is like moment of inertia, some span is given with the 2I, some span is given with the 1.5I. So first mechanism 1, we can take mechanism 1. So it is from A to B span. It is under the load. Here theta and theta, MP is the value. Delta is 6 theta. Delta is 6 theta. The load is 16 kilonewton per meter. So the internal work done is equal to, using the internal parameter of MP into 2 theta. Here it is the bottom point. In the left point and right point also the possible hinges form. So for the left point MP into theta, for the right point another MP into theta. So totally 4 MP theta is the internal work done. For the external work done, we know the area of the triangle into load. 16 into half into 16 into half, the span is 12 into h. So totally 576 theta. So if you equate internal work done with the external work done, 4 MP theta, which is equal to 576 theta. MP is equal to 144 kilonewton meter. So it is one of the moment of resistance value using the mechanism 1. Similarly, for the mechanism 2, so we already find under the 60 kilonewton load. Under the 60 kilonewton load, here it is 90. Here it is 90. So one point I have forgotten. The 16 is the ultimate load, using multiplying the load factor with the working load 5. So then only we can get the 16 kilonewton per meter. Here also we have to multiply with the load factor 90 into 3.2 and 60 into 3.2. So the span is 8. So here 8 theta is the deflection. Here 8 theta 1 is the deflection. And 2 MP is available here. In this theta, here it is theta 1. Okay. Theta 1. Now the internal work done is equal to, at the bottom of the load, 2 MP theta plus theta 1, 2 MP theta plus theta 1, plus here the intermediate support there is a possible hinge, but right side there is no possibility of hinge because of the simply supported. And MP into theta here, MP into theta here. Here only MP is available. Under the load only it is 2 MP is available. So we can make use of the relation previously formed. Theta 1 is equal to 0.5 theta for the second mechanism. I am using the relation here. 2 MP into theta plus 0.5 theta plus MP into theta. So 2 MP into 1.5 theta plus MP into theta. So 1.5 into 2 is 3 MP theta plus 1 MP theta is equal to 4 MP theta. So this is all about internal work done. So the external work done, load into deflection. So 60 into 3.2 into 8 theta plus 90 into 3.2 into 8 theta 1. Here also we can substitute 90 into 3.2 into 8 into 0.5 theta. Instead of theta 1 we can substitute 0.5 into theta. So totally the external work done is 2688 theta. When you equate internal work done to the external work done, 4 MP theta, which is equal to 2688 theta, the MP value is 672 kilonewton meter. So using the second mechanism, the moment of resistance is 672 kilonewton meter. From the first mechanism, it is 144 kilonewton meter. Next, for a third mechanism, mechanism 3, under the load of 90 kilonewton, possible hinge at B and under the load. Here it is 2 MP is available. Here it is theta 1, theta. We know the relation between theta 1 and theta. Theta 1 equal to 2 theta. Theta 1 equal to 2 theta. Here it is 60 kilonewton and 90 kilonewton. Multiplying with the load factor, you can multiply initially and you can substitute the value. So here it is 8 theta. 8 theta, 16 theta. Here it is theta 1. So now writing the internal work done at the left support MP into theta plus under the load 2 MP into theta plus theta 1. So MP theta plus 2 MP theta plus 2 theta. So 3 theta, 3 2s are 6. So totally 7 MP theta is the internal work done. The external work done is under the load 60 into 3.2 into 8 theta, because the deflection under the 60 kilonewton is 8 theta, and 90 into 3.2 into 16 theta. 16 theta. By considering this triangle, I have calculated the deflection as 16 theta. So totally 6144 theta, and equate internal work done 7 MP theta, which is 6144 theta. The moment of resistance is equal to 877.71 kilonewton meter. Kilonewton meter. For fully plastic moment, the highest value of moment is to be taken. For the collapse load, the least value should be taken. For finding the moment of resistance, highest moment of resistance value should be taken. Here it is 877, here it is 672, 144. So under the 90 kilonewton only, it gives maximum moment of resistance. So for fully plastic moment, the highest value should be taken. Highest value should be taken is 877.71 kilonewton meter. To find the collapse load, we have to take the minimum value. For the collapse load, we have to take the minimum value.